In this video, I'll talk about energy conservation in rotation. Energy conservation in rotation. So, try to understand. I'm taking one example directly such that to make you understand. Let us take there is a question like there is a pulley and this pulley is having mass m and pulley is in the shape of a disc, okay, and radius of that disc is r, and there is a weight of mass m and of course mass 2m are attached to the string which is passing over a pulley. So now my question can be, let's say we release these blocks from rest. So let's say this block of mass 2m comes h height down. Then my question can be find out the value of velocity of the two blocks while there is no slipping between rope and pulley, okay, and assume strings are massless, okay. So this is our question. So how to solve such type of question? This is the question based on rotational motion, okay. So you need to understand why everything is happening. So basically if this mass 2m comes down h height, because this is the same string, that's why this block has to go up to the height h only, correct? So now if there is no friction, there is no energy losses, then I can say that delta U loss for mass 2m. So basically this mass 2m will lose some potential energy. Because of this potential energy, what will happen? This mass probably will gain certain velocity v, and of course because string is same, that's why this block will also attain the same velocity, and this block of mass m will also gain some potential energy. That means delta U gain for mass m plus delta K gain for mass 2m plus delta K gain for mass m plus further anything is also happening that this pulley will also rotate with certain angular velocity omega, okay. So that means there will be some change in kinetic energy, so there will be delta gain for pulley, and obviously this is a fixed pulley, so it is not changing its direction, its height, so potential energy will not be changed. So now these all terminologies you need to find. So delta U loss for mass 2m is how much? That would be 2 mg into h. What is delta U gain for mass m? That would be simply mgh. Delta K gain for mass 2m, that is half 2m into v square, which is simply mv square, and delta K gain for mass m, half m into v square, right? And delta K gain for pulley So now this is the rotational motion, so that is given by half I into omega square. Suppose is the point O, then a moment of inertia will be about point O. That would be the value of rotational kinetic energy, right? So now we can substitute the values in order to find out the final answer. So let's substitute. So 2 mgh is equal to mgh plus half mv square plus mv square plus half io omega square. Now we have to put the value of I naught. So I naught, because this is a shape of disk, so that would be m into r square by 2. Okay, that would be given by mr square by 2. And they have said that there is no slipping. For no slipping between the rope and the pulley, so if you draw, this is the pulley, so this pulley is rotating with angular velocity omega. So this point P will be having velocity omega into r because of the rotation, right? And this will be Vp. And of course, because of the translational motion, because of this block is moving with velocity v here, so of course this velocity will be v. So Vp is omega r and Vp is v itself. That means v is equal to omega into r. So we can, in future, we can utilize this relation. So let us remove this segment now. So finally this will be, this is 2 mgh, so 2 mgh we can take that side, equal to half, this is half mv square plus mv square, so this will be 3 by 2 mv square plus half mr square by 2 into omega square. Correct? This can be written as 3 m by 2 mv square 1 upon 4 m omega r whole square. And we have proved that v is equal to omega r, so we can substitute this value further. So this will become mgh is equal to 3 by 2 mv square plus 1 upon 4 mv square. Take the LCM, this is 4, 6 mv square plus this is how much, mv square, so 7 mv square by 4 is going to be the value of mgh. So now we can solve this. Mgh is equal to 7 mv square by 4, so this m is cancelled out. V is equal to 4gh by 7 under root. So we achieved the velocity of the block. So v is the velocity of the mass 2m and simultaneously of mass m at that moment when it is vertically h height down. Okay, so I believe that you learned how to apply energy conservation in rotation. I can take one more example to make you clarify further. So let us remove. Let's take example number 2. So here there is a fixed pulley, there is a block of mass, let's say m, and string is passes over a fixed pulley like this, and there is another pulley and there is a mass of 2m, and then there is another pulley which is fixed with the wedge, and then there is another mass of, let's say, m by 2. Okay, now this pulley is having some moment of inertia I. Okay, this time they have provided the moment of inertia of this pulley is I, and this is pulley number 3, and obviously this is a movable pulley, right? Movable pulley, correct? This is a movable pulley. So now my question is that find out velocity of mass 2m when it goes down h height. Okay, and assume no slipping anywhere. Suppose that we have also connected a thread, so basically this block is not moving. This is given in the question. So if this is given, that means velocity at any moment of this string will be 0 because this is not moving. So simultaneously velocity is going to be 0 for this end also, right? And here this block goes, let's say, h height down, so I assume velocity is v. So if velocity is v for the block, then pulley will also have the velocity v downwards at that moment. And if for a movable pulley we can apply the relation that pulley is having velocity v, this end is fixed, it is having 0 velocity, then we can assume this end is having, let's say, x velocity, and I assume the direction is x. So we apply for a pulley, movable pulley, acceleration will be a1 plus a2 by 2, and vp velocity of the pulley will become v1 plus v2 by 2. This is we know from dynamics. So if you apply v pulley, which is v1 is x by 2, so x will be simply is equal to 2b. So I can write this rope will come down with 2v velocity, then this block will move with 2v velocity. So we have identified our relations with x and 2v, and now we can apply the energy conservation. Right? So if you apply the energy conservation, so basically because of a loss of potential energy of mass 2m, everything is happening. So I need to write delta U loss of 2m is equal to delta K gain of 2m. So 2m mass is gaining some kinetic energy because velocity is v. Now talking about this pulley, so here another factor is important, delta U loss of this pulley also, because this time you can see this movable pulley is coming h distance or h displacement down, and simultaneously this pulley is also gaining certain kinetic energy. So delta K pulley, okay, which is for rotation, plus obviously this and this mass is fixed, so there is no change, and even potential energy is not changing. So for the mass m, we can write delta K gain for mass m, correct? So now let us write down the values, what values we are having. So delta U loss for mass 2m, that would be simply 2mgh. Delta U loss for pulley, we will have, as pulley mass is, let us take pulley's mass is m, so if pulley mass is m, then it will be mgh, correct? And here delta K gain for mass 2m would be equal to half 2m into v square, that will be mv square. Delta K gain for block of mass m will be half m into 2v square. That means this is 2mv square, right? And delta k gain for the pulley. So for the pulley, you are seeing that if you talk about this point, so this point P is having 2v velocity downwards, and let's say this pulley is rotating with angular velocity omega, then we can write as there is no slipping, then because of the no slipping, this velocity will be omega into r, right, for the pulley. And I can say here this omega into r will be is equal to 2v this time. So omega and r will not be equal to v. Here it is equal to 2v, correct? So we can write delta k pulley rotational will be half I. So I into omega square. So now this I is also provided. So we can write I into omega square. Omega can be written as 2v by r whole square, and this will be 2I into v square upon r. Okay, so now we can substitute the values. So this was delta U loss only. So delta U loss is how much? mgh plus 2mgh is equal to delta k gain. So delta k gain is m into v square plus for the pulley 2iv square upon r plus 2m into v square. Now just solve this thing and you will be achieving your answer. So let us do that. So this will become 3mgh is equal to mv square. So mv square plus 2mv square will become 3mv square plus 2iv square upon r. Perfect. So here v square I am taking common. This will give you 3m plus 2I by r. So this is 3mgh. Now we can calculate the value of v, which is 3mgh upon 3m plus 2I by r, and of course under root of this. So this is going to be the velocity of the block 2m after coming down h height. So energy conservation is pretty simple. Just we have to take into the consideration of all energies, specifically kinetic and potential energy. If friction is also included, then you have to just consider the work done against the friction, because obviously some energy will be lost in the friction. So even though you can also calculate that also. So I believe you learned energy conservation and rotation pretty carefully. Okay, yeah.